This is our first lesson in 1.1. Before this was introductory, it was all about computers. And the learning objective of today's lesson is number systems. And this we will be discussing denary, binary, and hexadecimal, and their conversions respectively. If you see here, it's only a few pages in the book. So make sure you go home, read it again. There'll be something that you want to ask. But I made it as simple as possible. And even though I made almost 90 slides from these few pages, just to make sure you understand every single step. So I made it very small chunks. Let's see. If you have any questions, raise your hands. Okay, so recap. What is computer science? Last time we studied. So recap from the previous lesson. Raise your hands, don't answer it. What is computer science?
It's the study of how computers work.
Study of how computers work?
It's the study of how computers interact with humans.
Okay, anyone else? Yes.
What's the question?
What is computer science?
Science of studying computers.
Science of studying computers and computational thinking, okay? So it's basically study of computers and computational thinking. Number system, this is the outline of a lesson. Number system, activity, and solution. Yes. Okay. Second question we have, why do we study computer science? Very good. We use computers in every field of life. It's very important, okay? And what is under the hood of computer? So I'm going to go from here. We need to just one part of the computer, only one. Okay, a few of them I'm going to ask. Hard drive. PSU.
Graphics card.
Graphics card. Motherboard. RAM. Processor. CPU. You're not in there. GPU. Okay. Okay, so now what we do is we have, remember, denary system, binary system, hexadecimal. So all these questions we're going to answer. I want you to write down as well. Open your notebooks. I want to, because I have made these points, bullet points, make it shorter. So I want you to write this down. I'm going to explain this first, and then you write these down as well. This is going to help you for the exam. So the first one we have is we use this in our daily lives. The second one is called base 10 system, and it uses digits from 0 to 9. And the units in denary system is called ones, tens, and thousands, and so on and so forth. So it's going to go like this. Each time the unit increases by 10, power of 10, we're going to see that practically how it improves, increases. Yes. The next we have is, for example, we have 1, 2, 3. How can we explain this in detail? Can you finish this quickly in a couple of minutes? And then I'm going to go to the next slide and explain how we see this in real life and how it is in the background. Okay, how do we deal with these numbers? Okay, now the next slide we have is now how we write only 1, 2, 3, but how it's written actually is like this. We have 1, 3 here, 1, 2 there, and 1. And we said every single time we move here is going to be increased by power of 10. So from 3, we have 2 tens, and then we have hundreds. Go to next step. What we do is we draw this. Yeah, when I finish, then you draw it. Just now, pay attention. So what we do is, remember we said it increased by, so we start with, in computer science, we start with zeros, 10 to the power of 1, 10 to the power of 2. So we simply multiply this one. And the next step, what we do is, 10 to the power, anything power 0 is 1, anything power 10 to the power 1 is 10, and 10 to the power 2 is 100. So once we do that, so what we did here is, we got 10 from here, and we got 1 from here, because anything power 0 is 1, anything power 1 is 10, and anything power 2 is 100. And then what we do next step, we simplify further, 3, 20, and 100. And the last one is we add all these numbers, and this is, now it's okay if you don't write 10, but when we are dealing with two number system, then we have to make sure that we have the right base, so we can know which one are referring to which one. Okay, so this is You can write this down quickly. Just make a table. You can just write this part only. You can write this part, you can make a table and this one. Okay? Because we're going to use the same method on others as well. The same method we're going to be using on binary and hexadecimal. So what we're going to do now is we go into the binary. And binary, what we do, why do we use them? Computers use binary system. So computer understand only 2 digits as zeros and ones, which is called base 2 number system. And its use is only zeros and ones. The unit in binary system is increased by 2, power of 2. Earlier in denary or decimals, it was power of 10. Any number which is not in binary, anything denary or hexadecimal, has to be converted to binary for the computer to understand. So these can be another 4 points. That can be exam question. You can write this down, and then before we jump into more conversions of binary to hexadecimal. And at the moment, if you don't understand, it's fine. But by the end of the lesson, inshallah, you will be able to understand this.
I have a question. Do we have to memorize the Denary?
No, you need to learn it. You need to learn it. No, once you learn it, you don't need to memorize it.
But the Denary is a binary going to be easier?
Exactly, that's what I'm saying. By the end of the lesson, not today, the whole lesson, because it's just halfway, we're going to finish it. You should be able to just, if I tell you what is 12, then you should be just looking at it as 1, 1, 0, 0. The question is convert 1, 1, 1 binary number into a denary number. How do we do it? Let me explain step by step. When I finish, and I will ask you to write. So what we do, simply write down the number, and then what we do, we have to have the powers. 2 to the power 0, 2 to the power 1, so on and so forth. 1, 2, 4, 8. Second step. Third step, we simplify this one. So what we do, we get this number and multiply with, this number multiply with this one, this here, this comes here, this there. And then we further simplify it. 1 times 1 is 1, 1 times 2, 4, 8. And then we simply, last one, we add all these numbers, and that should give us a number. Now, earlier I said one thing to remember. Whenever you write this one equals this one, you have to make sure you have the correct base. So base 2, so 1, 1, 1, because it can be read 1111 if we don't have these bases. So make sure you have the base numbers correct. So this means this is in binary, this is not in decimals, and this is in decimals or denary, okay? So now you can write down, you can write this table, you can ignore the rest, write these 4 lines and these 2. You can write this down. Okay, now I'm going to give you this example. You can do this for me now. We said 1, 1, 1, 1. Yes. You make a table.
Yes.
Okay. He said 1, 2, 4, 8. That's our units. Okay. We want to put this here. 1, 1, 1, 1. Multiply this with this one, which is what? 1, 2, 4, 8. If these were one of them are 0, then what was going to happen? If one of them was 0, then this would be 0. Now we add all of them together. 1 plus 2 plus 4 plus 8 is 15. And now let's suppose I'm going to make this 0. 1, 1, 0, 1. What's going to happen is this is going to be 0. And it's going to be 1 plus 0 plus 4 plus this one is going to change what? 13. Do you see that? Okay, so can you do this for me now?
Yes, sir.
Yes. Don't get it. Which part? Which part? Conversion. So what's the unit we have? 1, 2, 4, 8, 16, 32. Which one? Which number do we want to convert? These ones. So what we do, we multiply this with this one, all of them. This is going to give us, this is binary number, this is going to give us 1 plus 0 plus 4 plus 8, because we multiply these two together. This with this, this with this, this with this, this with this. Now we add 1 plus 0 plus 4 plus 8 is going to give us a number 13. So now we can say in base 2 is equal to 13, which is in 10, because we change this to 0, yeah? 1, 1, 0, 1. So 1, 1, 0, 1 in base 2 is equal to 1, 3 in base 10. This one. This one is going to be, who has finished this one? It works like this. I'm going to do step by step. We did all the powers 1, 2, 4, 8. The next step I did is multiply all these ones with their powers. And then, can you see here 1, 2, 0, 8? Add all of them together. The answer is what? 8 is 11. Who said 8? 8 plus 0 plus 2 plus 1 is 11. Okay? And make sure you have the base correctly done. Now the next one we want to do is 8 bits. It's going to be the same procedure. The only changes we will see is in the powers. Earlier we did up to here, which was only 4 bits. Now what we do is 1, 2, 4, 8 is going to increase 16, 32, 64, 128. Okay. So what we do, if we have this number, which is 4 bits and 4 bits, 8 bits, the way we do it is similar, same procedure as we did with the other ones.
So we can do 7 bits.
7 bits.
We don't 8 bits, anything.
No, there's normally when you ask question that it is asked to change it in 8 bits. If you get sometimes 6 bits, we will see an example, then we have to add those 2 bits extra. The reason is, in real life, the system will take either 2 bits or 4 bits or 8 bits or 16 bits.
So the squaring rule applies to numbers like 8 bits, 7 bits.
The squaring?
Square the numbers, yeah?
These ones. No, these are basically, we studied in the beginning for base 10, we have base 2. This is base 2. Base 10, we were doing every single step we were going is going to increase by 10, base 10. But now it's going to be increased by base 2. So 1, 2, 4, 8, 16. So every single step you're going is going to be double of that, because in base 10 we were doing ones, tens, hundreds, thousands like this. But here it's going to be 1, 2, 4, 8. Every time we do it, it's going to double. But the way we do it is we simply write each number here under each power, and we simply multiply this with this, this with this, this with this. And then when we multiply this, we further simplify it. We have 1, 2, wherever the 0 is going to be 0. And we don't add them. And then we bring them further down. We add those numbers which are non-zero. We leave the zeros there. Another thing to note is when we're writing the answer, we have to write this is binary, but make sure you have the base 2 and make sure you have the base 10. So because we are dealing with 2 numbering system. So in this case, we will know which number belongs to which number system. If you go to another example, I was going to make you do this work, but because of the time constraint, I'm going to explain this. Yeah, time constraint. I'm going to show you this as well, because I was going to do this student activity. It was made for you, but let's do it together again. Now, this is earlier you were saying if it's more than 8, it's going to go to 16 bits, okay? Because that's, in real life, we remember I said the system is going to take 2 bits, 4 bits, 8 bits, 16 bits. And the rest, if you don't have them, we put zeros on the left-hand side. So that won't make difference, but the system will get full numbers.
What's the highest bit? Like, highest one?
Just every single time multiplies. There's a 16 bits, and then you have next one is 32 bits, then 64 bits, 128 bits. The thing is, implementation is going to be expensive, because as you go all bigger, then implementation is going to be expensive in hardware, in terms of hardware. Yes?
So it says here the 2 to the power of 14 is 16,284.
16,284.
It's
300. Well done. Good. Excellent. So remember, we had one rule where we say.
Sir, are we supposed to write any of this? No.
No, no.
Mister, should I be class?
So remember one. I am following one of my teacher's rule. If somebody finds mistakes in my slides, 3 mistakes, he gets some sweet. Okay. My teacher used to do that, and I got one as well once when I was in university. So that's yours. One. No, that's one only. Next lesson, if you find 2 other mistakes in my slides, then you can point it out, and then you will get sweet at the end. Other class, they got 1 sweet. 1 person got sweet so far. Sorry, said.
Do you decide how many bits to use depending on how large the number is?
Yeah, it depends on the system. If your system needs these many particular bits, then you have to get that one, because if your system needs 16 or 14 or 10 bits and you're using 8-bit system, it won't work. So you can make it exactly same bits or bigger, you can't make it smaller because you can't work. It won't work. Next one, what we want to do, exactly same procedure what we did earlier, 1, 2, 4, but this time because 16 bits, we're going to go up to 2 to the power of 15. We put those numbers which we want to convert to Denary numbers. Same thing with multiply them with respective numbers. Wherever there are zeros, they're going to be 0. We add them finally and add them together. And the final bit, which is important when you're doing an exam as well, when you're writing these two, make sure the base are correct. Okay, next slide. We want to convert 12 to binary. Well, how do we do that? There's one way that I'm doing here. There's another way which is in the book. I found that complicated, so that's why I'm going with this one. There are other ways as well. You can implement any one. I'm going to tell you the last slide to write it, not this one. Okay. So what we do, we simply write 12 here, and because we are going this transferring into binary, so we have to write 2. When we go into Denary, we were doing 10.
Why do you do that?
Because we are going into binary system. When we're going into Denary, we use 10, and for hexadecimal, we will be using 16. So what we do, 12 divided by 2, remainder is 0, and the whole number we get is 6. Next step, we get this number, now divide by 2, the whole number we get is 3. So basically another way we can say, how many 2's go into 6 is 3, remainder is 0. Next we said, how many 2's go into 3, 1 whole and 1 remainder. Remember, we don't want the decimal part, the dot 0, 0, dot 0, 1. We want whole numbers only. The next one we want, divide 1 by 2, remainder is 1, and the whole number is 0. Yes?
What if it's a prime number 13?
Doesn't matter, you will get the answer. Whatever number you give me, I can get you the answer for that one, okay? So now what we do, one thing to remember, we start getting the numbers from below. So we here, this number will go first, this will be next, this will be next, and this will be next. So the answer would be 1100. If other way around, it's going to be wrong answer. Again, 12 in decimals or binary number is equal to 1100 in binary. You can write this down now. You can write this down. It's stable. And so yes.
Is there always going to be a 0 in the top?
Not necessarily. If this is an even number, it's going to be 0. If it's odd number, it's going to be 1. But if this is 13, for example, it's going to be 1. If there's any prime numbers are normally odd or even. Prime numbers are what? Either odd or even. Always odd, yeah. 2 except 2. Now write this down quickly. I'm going to give you another example to solve as well. We have 9. Now here, earlier you're asking question, is it always 0? It's not always 0. So 9 divided, how many 2's go into 9? 4 whole and 1 remainder.
0, 0, 0.
Let's see. Next one we have 4 divided by 2. We have 2 whole numbers and we have 0. Next we have 2 divided by 2 is 1 whole number and 0 remainder. And lastly we have, when you divide 1 by 2, we have 0 here and we have 1 here. Now we collect it from bottom to top. We have 1, 0, 0, 1. And similarly 9 in base 10 and 1, 0, 0, 1 in base 2. Yes?
So it's always going to be 1 at the start.
It's going to be either 1 or 0 based on the number. If it's even number, it's going to be always 0 here. If it's odd number, it's going to be always 1. Yes, you have to make sure you collect it from here. This one goes here first, second, third, and that's fourth, okay? Because if you do it the other way around, you will get wrong answer.
Still, was it the same?
In this case, it is, but in others, it won't. Okay.
I want to see.
Next one we do, that was 4 bits. I want to do 58, and I want the answer to be 8 bits. Because the question would be saying, convert this number into 8 bits. So what we do now here is, we send the same thing. We 58 divided by 2, we got whole 29, 0 remainder. 29 divided by 2, we have 14 whole number, 1 remainder. Now 14 divided by 2, we have 7 whole numbers and no remainder. Next we have 7 divided by 2, we have 3 whole numbers, 1 remainder, and 3 divided by 2, 1 remainder, 1 whole number, 1 remainder, and 1 divided by 2, 0 and 1. Now the question here is, it says 8 bits, convert to 8 bits. Now here we have 1, 0, 1, 1, 0, 1, 0. What should we do? I'm going to hide this. What should we do?
We will add 2 extra zeros to make it 8.
Yeah, we have to add 2 extra zeros on the far left. The reason is it won't make difference. But if we do it on the left side, then it's going to change. Because in real life, when we have a system which takes either 2, 4, 8, 16 bits, then if we give them 6 bits out of 8, the remaining 2, the system won't understand which one to pick from, either 1 or 0. So the safest way is to give them zeros.
So the number like 29 to 1 has to be equal to the number here. Like if this is 5, this has to be 5.
What do you mean by this one?
No, because like I thought that was 7.
No, this one you start getting the number divided by 2 every single time. Get the whole number, but we don't want the decimal part. We want the whole number only. We want to use the remainders. This is our question.
Use the 0, the first 0.
It's because what's the remainder if we divide 58 by 2?
0.
0, exactly. So we do like this, 58. I'm going to do the whole lot, not just one. So it's going to be what? 29 to, that's going to be 4, 1, 8 comes down, 9, 18, 0, 0. So what's the remainder is 0. Okay? That's how we do it. Okay.
Left the 1 remainder.
That's the second part. When we divide 29,
Even the
last
last.
one, is because here is supposed to be 0, but we don't need it. Don't need it. So we can't further simplify it. Whatever is left here, normally this number has to be smaller than 2. Remember one thing? These 2 are important. We add them on the far left. And finally, when we are writing the final answer, make sure you have the correct base. So this number is in base 2, which is binary, and this is base 10, which is Denary.
How do I know when do I add the last 2 zeros? Or what do I know?
Count them. 1, 2, 3, 4, 5, 6. And the question is asking 8 bits. So it depends on the question.
Teacher, why can't we now put the 2 zeros in the last?
Okay, very good question. Why don't we put 2 zeros at the last? So let me explain that. I'm going to go somewhere behind. So explain that easily for you. Here, just random example. If I put zeros here, let me go further back to get this example. If I put 0 here and 0 there, that's what you're asking, yeah? Why we don't put it here? That's what you're saying. So there's a reason. If I put 0 here, it's not gonna, what I said is not gonna affect the results. Why? Because next would be what? Power would be 256, and next would be 512, yes? And remember, when this multiply with this one, we get what? From here we get 0. From here we get 0. Remember, we multiply these 2 numbers. But if I do the same thing here, what's going to happen? We have to change this whole lot because the power starts from 2 to the power 0. So basically you have to shift them 2 places. And everything, the value will change. Currently, if I change this to bring this one to there, then this will become 2 to the power of 2, which is going to be 4. So 1 multiplied by 4, see, we had 1 here, but it's going to change to 4. So everything will be changed. So it affects the results, but here it doesn't. Because we have to just follow on with the powers. There we have to skip all of them into that side, and it's going to affect the results. Got it? Any other question? Yes.
I don't understand like this question.
Same thing here. How many 2s? This is supposed to be 4. How many 2s go into 9? This is 4. And 1 remainder. Remainder should be here. Not the back. Here. Here. Top. Yes. That's 1. Similarly here, 2. There's going to be 2 here and 0 there. It's going to be 1 here and 0 there. So this is basically you've done it wrong completely. But let me explain at the end, okay? Okay. Any question? Clear this one? Okay. Next one we have is Ahmad.
This was the question.
Sorry?
This was the question.
This was the question, okay. The question is, you said, can you see here we have 9. 9 divided by 2. So there are 4 2s going into 9, which are whole numbers, and 1 is remainder because 4 times 2 is 8. So 8 take away from 9 is 1. Next we have 4 divided by 2 is 2 whole number, and we have 0 remainder. Next we have 2 divided by 2, 1 whole number and 1 remainder. And finally we have 1 divided by 2. We can't have anything, can't divide it, and this is remained as 1. So the answer is, again, we have to write like this. Okay?
You also counted the one at the start, right?
Yes. So well done, boys. The way you are paying attention, so I'm very, very proud of you, mashallah. Well done, keep it up, okay? Good. Now, okay, we did this one. Now, no. We did not this one, okay. I want you now to this one. Do this one now on your notebook, and then I'm going to come around and check it. Yes. Okay, now I see only one mistake in most of your work. Almost done, but there's one thing missing. Only I saw one student who's done it correctly.
I didn't teach you.
Let me see. Yeah, let me compare this one here. Check your answer with this one. Did you put this 0 at the end or not? Check it. Who did it? Raise your hands. 1, 2, 3. Got 2 zeros. Supposed to be 1 0. Good, well done. That means you remember the question. It's very important because it gave us only 7 bits, but the one we had to add from ourselves.
So this is correct?
Good, excellent. Boys, okay, next one. Okay, you didn't understand? Let me get, okay. When we do all the division conversion, we count the bits 1, 2, 3, 4, 5, 6, 7. Now we go back to the question. It says convert it to 8 bits, but the answer is 7 bits. So what we do, we add 1 on the far left. Okay, that will make our answer correct because the question says 8 bits. Shall I go to the next slide? Okay. There's a method, another method in the book. You can go through that, but I found it very complicated, so I preferred this table method. See, but you can still go to page number 11, 12, go through it. If there is any difficulty, you can come back, we can discuss it. The next, you have to do this is a homework. Go home, and then you can try these ones. What is the largest Denary? It will take you probably around half a minute. That's how easy it is. But just think about it. The first one. The second one we have is conversion Denary 6 to 4 bits. Is the same procedure we just did. Convert number 10 to 4 bits. So this is your homework. Come back next lesson, next one. It's end of, I don't know, this is the second lesson in the week. So come to the next one and we will discuss that. Yes. No, go to page number 12, right? Page number 12, 11 and 12 is there. Page number 11 and 12 is there.
Teacher, I finished this tomorrow?
Yes.
How will I know the question? I write it?
No, it's on the book. Write page number 11 and 12. And these book 1, 2, 3. Question 1, 2, 3 is there. No, copy in the notebook because there's no space in the book. Do in the notebook. Okay? And then there's another way as well. Another explanation for bit 8 is similar, just a bit longer. It's page number 12, 13, and another 3 questions. So I think all of them shouldn't take you more than 15 minutes. All 6 questions. If it takes more than 16 minutes, that means you need more practice.
Can you remind us of the group?
Okay. Yeah, that's page another 12, 13, 11, 12, 13. So this is going to be question number, and I put this in the next week's homework as well. So if you do it, you will be covered with that. I already put those questions in the homework as assessed one, which is 10% of your overall grades, okay? So all these questions, all these 6 questions. Yeah, weekly plans. I have already put it there as well. So when you do it, then basically you cover. I don't know. Yeah, you can go through it. Yeah, 6 questions. But you don't have to wait for me to all answer a question. If there are extra questions, you should do it. If you struggle with it, we can come and discuss in the class. Yeah, do it because we are preparing for the external exam. On another one. Now the next one, we're going to the next system. Interesting one. And I have another rule. I don't know if you remember. Anyone find mistakes in my slides? 3 mistakes, they get sweet. You got 1, 2 more, then you can find a sweet. As one of my teachers used to do that, and it's very interesting. Good attempt, good try, but it's still correct.
Teacher, do I get my book tomorrow?
Computers can process hexadecimal numbers.
Computers cannot process hexadecimal numbers, humans can. Yes. Yes, it's correct.
Teacher, do I get my book?
Remember, computer understands only 2 digits, zeros and ones. So anything else, if it's hexadecimal, denary, everything has to be converted to binary before the processor processes. So hexadecimal numbers, we have done so far denary, we have done binary, now we're going to the hexadecimal. Computers cannot process hexadecimal numbers, but humans can. This is a base 16 number system. So far we have done base 10 and base 2, and base 16 use 16 symbols. They are from 0 to 9, the numbers, normal numbers, and A to F characters of English alphabet. The unit in hexadecimal number system increased by power of 16. Remember, in binary it was power of 2, and in denary it was power of 10. Like denary numbers, hexadecimal numbers also need to be converted. So anything apart from binary numbers have to be converted to binary for the processors to process it. We have the denary numbers. You can go further down, and then we have binary. It can go as well, and then we have hexadecimal. If you notice here, one thing to notice is up to 9. These are the same numbers, yes. But here, you should remember this one only. 10 is equal to A, 11 B, and 12 C, 13 D, 14 E, and 15 F. So you should remember these numbers. This is important. Whenever we do conversion, you need to know these numbers, yes.
So does that mean if the number is 16 and hexadecimal will be, for example, A0?
If number, no, it's up to 15. Because if you go to 15, for example, from 0 to 9, you write only one digit. But when it goes to 10, it becomes 1 and 0, it becomes 2. Similarly, if you go to 16, it's going to become 2 digits.
Does that mean that for hexadecimal is only up to 15?
Yes, 0 to 15. That's it. That denary number is 0 to 9. And binary is 0 and 1. How do we do conversion? The question can be an exam. It's convert hexadecimal to B3 to denary number. How many have done this conversion before? Raise your hands if you've done it before. This conversion, no? Let's do it. Pay attention, pay attention. What we do is create a table like this. Write the number we want to convert. Second one, the reason I left the top one is empty is because we're going to be using the powers. So earlier we were using what? 2 to the power of 0. That was base 2 conversion. Here base hexadecimal, sorry? Say it again. Yeah, with practice it will become easy. So here is 16 to the power of 0, 16 to the power of 1, which is 16, 16 to the power of 2, which is 256. Then what do we do next? It's going to be the same procedure. The only change has happened here is power of 16. Earlier it was power of 2. Now the next step, what do? We bring this number down, which is in the question, and we bring this power down. In the beginning, you write it like this, but when you practice enough, then you can change this into simple 1, 16, 256. The same way we did it with binary. Instead of writing 2 to the power of 0, 2 to the power of 1, we just wrote what? 1, 2, 4, 8, 16, 32 like this. So with that comes with practice. Next, we write this B here 11. Remember we just said previously, B is equal to 11. A is equal to 10, B is equal to 11. So when we can doing conversion, we have to bring it back to normal denary number. And then this 16 comes down here. So we multiply that. Next, we bring this 2 down. We don't need to change it. 11 is, remember, we said hexadecimal 10 is equal to A, 11 is equal to B, 12 is equal to C, and so on and so forth. You need to memorize only these six digits, yeah? 6 characters. The rest.
Oh, okay.
If you go back, let me take you here. You see here, only these ones. You need to memorize these one to which one is referring to which. Going back, okay, this step is clear so far, yes? Next one, the final one. We simplify this one. 1 times 3 is 3. 11 times 16 is 176. And then 2 times 256 is 512. That's the final step is what we do. We add these numbers together. We add them together, it's going to give us 691. And lastly, I'm re-emphasizing on this one. We write the question again 2B3, but remember the base. We are going from base 16 to base 10. And here, these bases are very important. In this case, we can see the left-hand side is a hexadecimal number because of the B. But sometimes you will get a number which doesn't have characters, ABC characters. It's just simple numbers, but they have to be changed. They still are hexadecimal numbers. So that will be, this will decide which number we are referring to. So make sure you write those down. Quickly write this down, and I'm going to give you example to practice. Quickly. Let me do again quickly. We have a number which is hexadecimal, which is 2b3. We need to convert it to Denary. How do we do that? We write the table like this first, and then we write the question. This is the question, yeah? So the question exam could be, convert this number into binary, in the Denary. And what do? Is we write 16. Remember we said this is going to change by power of 16. So 16 to the power of 0 is 1, 16 to the power of 1 is 16, and then 256. What we do next, we bring this here and bring this there. B is 11. What is B? Go back. You weren't here, that's why. Denary numbers are these, but hexadecimal are these. Up to here, they are same, but here, these ones, you have to memorize. You have to learn. 10 is A, 11 is B, because hexadecimal has only 0 to 9 and A to F. Going back. So, what we did, this comes here, this goes there, 16 here, 2 to 56. Next step, what we do, simplify this, simplify this, simplify this, and add all these numbers. What we have is 691, and remember 2b3, which is a hexadecimal, that's why it's base 16, is equal to 691 in base 10. Ahmad, correct?
Yes, I got it.
Clear? Now, next example, do it quickly. I'm going to give you 3 minutes.
So what is A as a number?
A is 10. Remember, boys, A is 10 in the table, and C is what? 10, 11, 12. 12, yeah? And 3 is 3. 3 is 3. Okay, boys, check your answers here now. Can you see here? We have A, 3AC. So we multiply, this is 12 with 1, 10 with 16, and 3 with this one. Yes. Next step, we have multiply this 12, simplify this 160, simplify this 7, 6, 8, and add all these 3 numbers. We get 940. But remember to put the right base. So 3AC in base 16 is equal to 940 in base 10. Okay? How many of you got right?
Yes.
Well done, well done, good. We go from hexadecimal to binary. We went to Denary first, now we want to go binary. This is easier compared to that one. What do we do that? We write this which is in the question, 5E. You can go from here directly to there, it's fine. But the reason I did it here just to make it easy for you to understand. So what we did here is, you need to remember one rule about this one. Every single hexadecimal number or character is equal to always 4 bits in binary. Remember the rule. Every single character or number in hexadecimal is always equal to 4 bits in binary. So I'm going to explain how. So we have 5 and E, a number and a character. So E is equal to what in normal numbers?
14.
14, which is, and remember how do we do when you become expert in conversion, you simply do like this, 1, 2, 4, 8. Remember, 1, 2, 4, 8. So 1, 2, 4, 8. 1 multiplied by 0 is 0, and then 2, 4, add all these numbers, so it's going to give us 8 plus 4 plus 2 is 14. Okay, done?
Yeah.
Second one, we have 5. How do you write 5? 1, 2, 4, 8. 1, 2, 4, 8. These are, remember, these are the powers, 2 to the power 0, 2 to the power 1. So I write it in this format. Now, this multiplied by this is 1. 0 multiplied by 2, it cancels because 0 times 2 is 0. 1 times 4 is remain there, and 0 times 8 cancel. So what do? We add only these 2 numbers, 4 plus 1, which is 5. Can you see here? So basically we do the reverse calculation. Is this correct or not? And then what we do, clear that. So far we have come here. Finally, what we do is just remove the space. The reason I put the space here for your understanding, you don't have to do that, just to make it easy for you what we are doing here. So we remove the space and combine them together, and that's it, khalas. Okay? Now one thing to remember. When we are writing 5, for example, 1 is equal to 1, 2 is equal to 1, 0, 3 is equal to 1, 1, 4 is equal to 1, 0, 0. 5 is equal to 1, 0, 1. We could write 1, 0, 1 here, but I wrote 0, 1, 0, 1. 0, 1, 0, 1. Why? The reason is?
4 bits.
4 bits. Good, you remember. The reason is it was 4 bits, that's why we had to add 1 0 there. Because it's a requirement that every single character or number in hexadecimal has to have 4 bits. Okay, clear?
How do you multiply? Like 2, 4, 1?
If you go back, when we were doing conversion, in the top, what was it? 2 to the power of 0 is equal to 1. 2 to the power of 1 is equal to 2. 2 to the power of 2 is equal to 4. So instead of writing the whole bit, the whole equation, we just write 1, 2, 4, 8, 16. So when you become an expert, you don't have to write the whole table. Just write 1, 2, 3, 1, 2, 4, 8, and then multiply it. So the same thing we did. 1, 2, 4, 8. Multiply these, and then once you do that, cancel, and then add them. So everything is multiplied, and then add them, and then we get the answer, which is E. In this case, which is 5. Yeah? But it comes with practice. It comes with practice, yes? Yeah, it comes with practice. Okay, write this down. I'm going to give you another example. Write this down quickly.
What is 4 equal to?
4 equal in binary is 1, 0, 0. See, when you practice enough, you just know it straight away, very easily. And how do we know? Is look, 1, 2, 4. So 1 is cancelled, 2 is cancelled, 4 is the only. So, yeah.
Memorize.
And not memorize, you learn it. Because memorization will get a problem. But when you learn it, what is 1 is equal to what? Let me clear this. This is how you do it. In binary, 1 is equal to 1, normal denary. 2 is equal to what?
0.
1 and 0, not 0, 1 and 0. Again, why? Because there's a placeholder for 1, this is 2. So this is cancelled, we get 2 back. 3 is equal to what? 1, 1. If you see here 1, 2. 1 times 1 is 1 plus 1 times 2 is 2. So add them together, we can come back. So I'm doing conversion reverse, converting from 3 to 1, 1 and 1 to 3 again. And then similarly we do 4. 4 is equal to what? 1, 0, 0. And the same thing, 1, 2, 4. This is cancelled, and we come back to 4 again. So I'm doing same time. But this comes with practice. And the 5, next one we just did, 5 is equal to 1, 0, 1. Because this is 1, this is 2, this is 4. So this is 1 times 1. Cancel 1 times 1 and 4 times 1. Add them together. 1 plus 4 is 5. And then 6, what do you do with 6?
1,
6 is what? 1?
1, 1.
And?
1, another 1.
No, that's 7. That would be what? If you say 1, 1, 1, that means 1 plus 2 plus 4. But here, 0 plus 2 plus 4, 6. 7 is 1, 1, 1. So 1 plus 2 plus 4. Okay?
Then 8 is 1,000.
8 is, you don't say it 1,000 binary, we say 1, 0, 0, 0. Okay, that's the difference. So you should remember this one. That's the main thing you should remember. You said what to remember in binary? Remember the powers. 1, 2, 4, 8, 16. So basically what happens is it gets double every time. You should remember this part. In binary, the powers. In tens, what do we do? 1, 10, 100, thousands. Can you see here the pattern? In hexadecimal, what we do? 1, 16, and then next one is 256, and then so on and so forth. Okay? So you remember these, memorize these, the rest you need to learn. Okay, next question. Can you do this for me now? Come in there now. Come on, you have a few minutes. 2 minutes, 2 minutes, 2 minutes. A is 10. Yes, A is 10. If you get this one right or no. So what you do, we write like this, split it. What is 2 in binary?
Oh, okay.
So you're missing what? What are you missing here? Exactly. Remember what we said in the beginning? Every single hexadecimal number has to have 4 bits. So here, some of you were missing these 2 numbers, these 2 zeros. So 2 is equal to 0, 0, 1, 0. 1 is equal to 1. 0 is equal to what? 2 is equal to what? 1, 0. You need to know these ones.
It's a binary, it's only 1 and 0.
So 1 and 0. 3 is equal to what?
0,
1, 1.
1 plus 2 is
4. What is 4?
0, 0, 1.
You can't say 100. It's going to be 1, 0, 0. 5.
Yes.
Okay. So if you got this right, go to next one. So remember, this is 2, which is 1, 2, 4, 8. Cancel, cancel, cancel. Only 2 is left here. And A is equal to what? 10. So this is 8. This is 2. 8 plus 2 is 10.
From in the hexadecimal from A, B, C, continuous 10, 11, 12, 13, 14, 15, and above.
Up to 15. Up to 15, okay? Because when you go to 16, it calculates. That's another number now. Okay? So what we do now here, we're going from binary to hexadecimal. Remember one specific rule for converting to a binary to hexadecimal or hexadecimal to binary is one hexadecimal number or character is always equal to 4 bits in binary. Remember that one. So here what we did,
How do you remember the digits?
just 4. You will. What do you mean by remember digits?
1, 1, the pattern.
The pattern I remember I told you how to do it with binary is 1, 2, 4, 8. So these are the powers. Give me any binary number, 4 bits. Any? No, in binary. 4 bits, for example, this is binary, yeah? 4 bits. So 1, 1, 0, 0. So what we do is we cancel out.
8 plus 4.
Basically, these two, this is multiplied with this one, this is multiplied with this one, this is multiplied. These are powers, yeah? 1, 2, 4, 8. And this is multiplied with this one. And then once we do that, this one is cancelled because anything multiplied with 0 is 0. This is cancelled. We add these two numbers. So 4 plus 8 is equal to 12. That's how we do it. So you remember it as you practice.
Mr. So like, it's like you do it normally, but like 12. I don't understand.
Let me explain this one now.
13, 12.
Let me explain this one now. First, we separate them as 4 bits because we said every single hexadecimal number or character is equal to 4 bits. So we did 4 bits.
12, 4.
Next, can you see here we separate them? And then I've done this extra step just to make it easy for you. 4 different bits, 4 bits into 3 parts. And then this one is equal to what? 1, 2, 4, 8. So 8 plus 4 is 12 plus 1 is 13. So this is 13. And 1, 2, 4, 8. So this is 4. 1, 2, 4, 8. 8 plus 4 is 12, which is C. Exactly. Yes, yes.
But instead of just using denary numbers, you use the C, 4, D, and like.
Because we're going from binary to hexadecimal, that's why. So lastly, what we do, we write this as with base 2, and with this is base 16. Copy this one down, and I'm going to give you one example for practice. You see here, in binary, what we said, 2 to the power of 0 is equal to 1. 2 to the power of 1 is equal to 2. 2 to the power of 2 is 4. And 2 to the power of 3 is equal to 8. We can write it like this, or we can write like this as well. 1, 2, 4, 8. Both are same thing. This is a bit complicated, this is easy. So 1, 2, 4, 8. And then whatever number you have, I'm going to take last one, okay? Write simply, I'm going to change the color. I write it here, 1, 1, 0, 0. So the next step what we do is we multiply these, okay? So that's going to give us what? 0. This is going to give us 0. It's going to give us 4. It's going to give us 8. Now we add them. We don't ignore these ones. These two are going to give us 12. And 12 is equal to C. Okay?
Okay, but how will I do it? I want to have the answer when I'm in the exam. How will I do it?
You simply memorize this one. This one. 1, 2, 4, 8. And you multiply them. Just remember, you have to memorize this line only. 1, 2, 4, 8. And 16 like this. You can do this. Copy this one.
No, I want to do this one like
Yeah, do it. That's fine.
Can you write that A for 2, 1? Like, can you skip the first step?
Yeah, you can like this. Yes. Yes. You can see how many bits look? 4 bits, another 4 bits. That's the first thing you do. You divide them into 4 bits, yeah? And then you do the next step and the next step.
Always in 4.
If it is like this, if it's not, then you have to add zeros to make it 4 bits, okay? So it has to be either 4 bits, 8 bits, 12 bits, 16, like this. If it's not there, then you have to make sure, because each 4 bits is equal to 1 hexadecimal number. This one is our 1, 0, 0, 0, 1. This one is 1, 2, 4, 8. So 8 plus 4 plus 1, 13. 13 is equal to D.
I used your method like before.
Exactly. 1, 2, 4, 8. 1 plus 8 is 9. Convert 350 denary into hexadecimal. What we do is write 350 first, and then the numbering system we are going into. So the first one is how many 16s go into 350, which is 21. So 21 times 16 is 336. The remainder is 14. The next step we have divide 21 by 16. We have 5 remainder and 1 whole number. Lastly, we have 1 divided by 16. We have 0 whole numbers and we have 1 remainder. And then, as we said before, we write it like 15E. 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 And then what we do is 350 in denary or decimals equals to 15E in hexadecimal. No, if it's something is bigger than 9, it will be alphabet. Something lower than 9 or lower than 9 is going to be 0 to 9. 0 to 9.
So why would 14?
14 is above 9. So remember in hexadecimal we have for 10 we have A, for 11 B, 12 C is like this, so on and so forth, up to 15, which is F.
Why would not say 14?
Because the remainder, when you multiply this number with this one, we will have a 336. Whole numbers 336. So 366 take away from 350, we got 14 remainder. This part is our answer basically. This part is our answer. Now the next example we have done this last time. And this is the example student activity. So I want you to do this quickly, and then we can go to the next part. I want you to finish this quickly. Convert denary to hexadecimal. Yes. We bring this number here, 471. And how many 16 go into 471 is 29. 29 times 16, we gonna get 464. So take a 464 from 71. It's gonna get 64 is gonna give us 7 remainder. Next, how many 16s go into 29? 1. 1 is a whole number. Remainder is D, which is equal to 13. And lastly, we have 1 divided by 16. We have a whole 0. A 0 is a whole number, and the remainder is 1. And again, lastly, we make sure we copy the number like this. So 1D7.
16 to 29 is 469.
464. So if you multiply this number 19 with this one, we're gonna get 464. 464 take away 471, we're gonna get 7 remainder.
13C.
There is 16, minus this is what you get as D. You multiply 1 with 16, then you minus that with 26, 29. 13 equals.
Isn't 13?
What we do is we divide this number by 16. The whole number we get is 29. What's the remainder? How do you find the remainder? Yeah, multiply these two, that should give us 464. And subtract this from here, you will get 7.
Isn't 13C?
Yeah, similarly we divide this by 16, we get 1 whole number. And this multiplied by this 16. 16 take away from 29 is going to give us a remainder of D, which is equal to 13. Okay?
Is D like it's 14 and C is 13?
From here, 1 times 16, 16 take away from 29, we get 13. It's because if, how many 16s go into 29? How many 16s go into 29? So this is our D.
15.
That's to make easy. How do you find? First step we divide, which we did. One is here. This one goes here, and this is the remainder, which is less than, always less than 16. So it's going to go there because the remainder is our final answers.
Teacher, can you skip to the other question?
Mister, how is it?
Respectfully, don't mean anything.
Now we're going. This is the last one. We're going to.
Mr. Can
Yes.
Is it 13C?
There's the how do you get the one again?
This one. The same thing here. We do this again. Same thing. We have 1 divided by 16. So basically we can't divide it. This is the remainder itself. So that is going there. So we can't do anything. So it's 0. Basically we don't write 0 here. But we can't divide it. So that is the remainder itself.
So is it 13C?
No, it's basically 1 D7.
No, like 13. It's like
No, 10A, 12B,
exactly.
10, 11B, 12C, and 13D.
Like you count 10 as A.
Yeah,
And then
exactly. So the last thing we have in the lesson, which is why is hexadecimal used? In the book is quite big. If you go here, in the book is quite big, but I have compiled them in small bits. And this is, if you see here, compact representation. This is one of the reasons. Easy conversion, which we just saw right now. Readability is easy compared to reading binary numbers. And common usage, we use it in memory addresses and in the websites. So these are the things you can go through it in detail. I have compiled them and made it easy for you. This is from a book. You can go through that again, just to make sure that you grasp everything. So far we have finished the lesson, but I have gathered some of the keywords from the lesson. In the book is only one-liner definition for it, but it's your activity. I leave it for you. Go through it. But we'll slightly discuss only the one-liner which we have seen in the book. The first thing we have is analog data. So analog data is the continuous data we have when we're dealing with data. For example, we have, in contrast to that, we have zeros and ones, which is discrete data. Continuous stream of data that is processed by humans. So we see in the EEG or ECG, we have a data which is continuous. That's one of the examples. The characteristics are here as well. You can go through that. It's your activity, student activity. We have continuity, finite value, and examples which are. So here, where do we use them in daily life? This can be an exam question. So I have gathered some information. So audio signals, temperature reading, video signals, analog clock, analog sensor. These are all different examples in our daily life that produce continuous data, analog data. The next we have is digital data. And what does digital data do? How do they look like? Is basically zeros and one, discrete form of the data compared to analog data, which was continuous. Yes.
digital data is like the hardware. So yeah.
Basically, it's based on zeros and ones.
So it's
Digital data. You can see an example here. Discrete. It is precise, like zeros and ones. In the continuous data, we have some data in between as well. It's not just highs and lows, but in between as well. And then examples we have is digital files, text file, digital images, digital videos. These are the examples for digital data. And where do we use them in daily lives? As we said, it's in text. As we said, it's in text file, digital music, digital images, and these are examples of digital data. Next one we have logic gate. Logic gates, we have complete chapter on it. We will be studying a whole chapter on logic gates, but just a brief, simple definition. These are very small components in computer systems that controls the flow of electricity. Next, we have registers. We will study that in detail as well in next coming chapters. A small component in computer system that stores data temporarily. When we are entering data in the processors, they are stored. I have done one project on here. I'll bring that as well, inshallah, in one of the lessons, where how the data go through the processor and use different registers before ALU and after ALU. Yes. And the next we have done this one with Denary number system, base 10 number system Denary. We have done that. The lastly, I think we have is MAC address. This is basically MAC address is media access control. Every single computer has unique address. It's network cards in the world. So they look like this. It's recognized when they are manufactured. That's when they are assigned these numbers, these media MAC number. So every single computer has it. Inside there is a network card, yes. Yeah. How is it 48? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why is it 48-bit, Yahya? Why is it 48-bit? Because, can you see here, these are all hexadecimal numbers. And we said each hexadecimal number is 4-bit. So these are 12. 12 times 8 is 48. That's why. So it's easy to memorize or read. Remember, we saw the properties of hexadecimal. This is the number for each MAC, each device, MAC address. This would have been, if you write 48, exactly. If you were going to write this in binary, that would be 48 zeros and ones. That's a lot. Okay. We will go through the worksheet 1 next lesson. And conclusion so far we have is we studied Denary, binary, and hexadecimal numbers.